The equation E equals mc squared is perhaps the most famous equation in all physics, but very few people actually know what the equation means or where it comes from. In this video, I would like to show one method for deriving this equation, as well as provide some insight into what the equation actually means. Along the way, we will also touch upon some of the most fascinating features of Einstein's theory of special relativity. So let's get going. The purpose of mechanics is to describe how bodies change their position in space with respect to time. Consider the following. I stand by the window of a train that is travelling uniformly and drop a stone, without throwing it, out of the window. What do I see? Well, disregarding air resistance, I would see the stone descend in a straight line, whereas a person who observes the stone from the side of the platform would see the stone fall to earth in a parabolic curve. So a natural question arises: do the positions traversed by the stone lie in reality on a straight line, or on a parabolic curve in space? Well, in the first place, we will stop using the vague word space, and rather talk about motion relative to a system of coordinates, which is useful for a mathematical description. We are then in a position to say the stone traverses a straight line relative to a system of coordinates rigidly attached to the train, but relative to a system of coordinates rigidly attached to the ground, it describes a parabolic curve. It is now clear to see that there is no such thing as an independently existing path, but only a path relative to a particular frame of reference. The fundamental law of the mechanics of Galileo and Newton can be stated as follows. A body removed sufficiently far from other bodies continues in a state of rest or uniform motion in a straight line unless acted on by an external force. This is called the principle of inertia. A frame of reference or system of coordinates which is in a state of motion such that the principle of inertia holds relative to it is called an inertial frame of reference. You can think of an inertial frame of reference as a non-accelerating frame of reference. This is the reason that Einstein's theory of special relativity is referred to as special, because it only deals with inertial frames of reference. And it is these special, inertial frames of reference that we will focus on in the remainder of this video. The principle of relativity was in fact introduced by the great Italian scientist Galileo, who used it in his dialogue concerning the two chief world systems. The dialogue was published in 1632 and consists of an imaginary conversation between three characters, one of whom, Salviati, tried to convince the other two of the validity of the Copernican theory that the Earth orbits the Sun rather than the other way round. Another character, Simplicio, puts forth various arguments against the Copernican view, all of which are deftly demolished by Salviati. One of Simplicio's arguments is that the Earth can't be moving around the Sun because it doesn't feel like we're moving. Surely if the Earth was moving, we'd know. Salviati disposes of this idea via a simple thought experiment. He asks the reader to imagine shutting themselves in the main cabin below decks on some large ship and performing a series of simple experiments as the ship proceeds with uniform motion in a straight line. He notes that you will discover not the least change in all physical experiments, nor could you tell from any of those experiments whether the ship was moving or standing still. He concludes that because there is no way of performing an experiment to distinguish between a stationary frame of reference and a frame of reference moving at a constant speed in a straight line, there should be no difference in the laws of physics used to describe the motion of objects within those frames of reference. We will therefore assume that the principle of relativity holds true, and assume that the laws of physics should be the same in all inertial frames of reference, which are simply frames of reference that move at a constant speed relative to one another. Let us now suppose that a train is travelling along a railway track with a constant velocity z relative to the track, and that a person on the train is walking in the direction that the train is moving with a velocity w relative to the train. What is the person's velocity v relative to the railway track? Well, we see that if the person was to stand still, then during 1 second they would travel a distance of z meters, which is the distance the train travels in 1 second relative to the track. By walking, the person traverses an additional distance of w meters in 1 second. Thus, relative to the ground, they travel with a velocity of w plus z meters per second. This is referred to as the Galilean addition of velocities. Let us now think about the consequence of applying this idea to the propagation of light. One of the first things that you're taught in school is that the propagation of light in a vacuum takes place in a straight line and with a fixed speed of 3 times 10 to the 8 meters per second. This follows from Maxwell's wave equation, which contains information about the speed of the waves in terms of the constants of the theory. But when we say that light propagates at 3 times 10 to the 8 meters per second, which reference frame are we referring to? Although Maxwell's equations predict the speed of light, they do not tell us which frame of reference this speed is referred to. To emphasize this point, let us take the train as our reference frame once again. We will assume that the train is moving with a velocity of z meters per second relative to the track when a pulse of light is emitted on the train with velocity c meters per second relative to the train. This situation is analogous to the situation where a person is walking on the train. We simply replace the person with a light beam. So the natural question arises, what is the speed of light relative to the track? Adopting the same logic as we did with the person walking on the train, one is led to the conclusion that light is travelling with a speed c plus z meters per second relative to the track. In other words, the speed relative to the track is greater than 3 times 10 to the 8 meters per second. But this appears to conflict with the constancy of the speed of light implied by Maxwell's equations. To make this point a slightly different way, consider another example. Is it not evident that if you are in a car travelling at 20 meters per second relative to the road, and a car travels past at 30 meters per second relative to the road, then the speed of the second car relative to the first car is simply 10 meters per second? Then surely it's also true that if a spaceship is travelling at 200,000 kilometers per second relative to the road, and a beam of light travels past at 300,000 kilometers per second relative to the road, then the speed of light relative to the spaceship is 100,000 kilometers per second. But if you actually were to do the experiment, this is not what you would find. When you do the experiment, it looks as if the light is travelling 300,000 kilometers per second relative to the spaceship, and it looks as if the light is travelling 300,000 kilometers per second relative to the road. So how can both of these statements be true? Einstein realised that the only possible way in which a person standing still and a person moving could measure the same speed of light is if their sense of space and time was not the same. In other words, relative to the spaceship, the light is travelling 300,000 spaceship kilometres per spaceship second, and relative to the road, the light is travelling 300,000 road kilometres per road second. How can it be that one person's measure of time is different from another who is in constant relative motion? To answer this question, we will have to think about what it means to measure the duration of time. Let us consider a very simple kind of clock. It consists of two perfectly parallel mirrors separated by 1 meter. And if we send a light signal between the two ends, the light keeps going up and down, reflecting off the mirrors, making a tick every time it moves up and a tock every time it comes down, like a standard ticking clock. We build two such clocks with exactly the same lengths and synchronize them by starting them together. Then they agree always afterwards because they are the same length, and as we've seen, light always travels with the same speed, c meters per second. If we give one of these clocks to a person to take on a train that is set to move at a constant velocity relative to the platform, and they mount the clock perpendicular to the direction of the train motion, then what we want to do is consider how this moving clock compares to a stationary clock. We can calculate the time taken for the tick-tock of the stationary clock, which we call t0, by noting that light travelling at speed c travels a distance of 2 meters during one tick-tock of the clock, and therefore the time taken for the tick-tock of the stationary clock is 2 over c. What about the clock that is moving on the train? When an observer stood at the side of the railway platform looks at the moving clock, they will see the light take a zigzag path in going from mirror to mirror, as can be seen in the diagram. We immediately see that due to the motion of the train, the path taken by the light during the tick-tock of the moving clock is longer than the path taken by the light during a tick-tock of the stationary clock. If we assume that the train is moving with velocity v meters per second relative to the platform, and if big T is the time taken for light to travel from bottom mirror to top mirror, then we see that the train will move a distance vt during the time it takes for a tick of the moving clock. We also see from the diagram that the distance travelled by the light beam during this time is ct. Because the train is moving at a constant speed, the same is true for the tock of the moving clock. Now, if we look at this diagram carefully, we see that there is a right-angled triangle involving vt, ct, and the distance between the two mirrors, which, if you remember, is 1 meter. And so we should be able to use Pythagoras' theorem to find a relationship between the three sides of this triangle. If we focus in on this right-angled triangle, then we can use Pythagoras' theorem, which states that the square of the hypotenuse of a right-angled triangle is equal to the sum of the squares of the other two sides. Applying this to our example, we see that ct squared is equal to 1 squared plus vt squared. And if we rearrange for t, then we find that the time taken for a tick of the moving clock is 1 over the square root of c squared minus v squared. But we want the time for the tick and the tock of the moving clock, and so we need to multiply this by 2. If we use lowercase t for the time taken for the tick-tock of the moving clock, then we see that t equals 2 over the square root of c squared minus v squared. Next, if we take out a factor of c squared inside the square root, we can then write t as 2 over c divided by the square root of 1 minus v squared over c squared. The reason we have done this is because 2 over c is none other than the time taken for the tick-tock of the stationary clock, which we labelled t0. And so we see we can write t equals t0 divided by the square root of 1 minus v squared over c squared. This expression is often written in the compact form t equals gamma t0, where gamma is the factor which tells us how significant the difference is between t and t0. We will see that gamma pops up in many of the modified equations of relativity. So, what is this expression telling us? Well, the first thing we notice is that if v equals 0, then gamma is simply equal to 1, and we see that t equals t0. This is simply telling us that if two clocks are stationary with respect to each other, they will tick and tock at the same rate. If, on the other hand, v is greater than 0, then the square root appearing in the expression for gamma will be less than 1, and therefore gamma will be greater than 1, and so the time taken for the tick-tock of the moving clock will be greater than the time taken for the tick-tock of the stationary clock. Now, it is important to emphasise that not only does this particular moving clock run more slowly, but if the principle of relativity is correct, then any other type of clock would also have to run slow by exactly the same amount. Well, why? Because otherwise the person on the train would be able to use the mismatch between the clocks to determine the speed of the train, which would violate the principle of relativity, which we have already seen states that there is no way of performing any experiment to distinguish between a stationary frame of reference and a frame of reference moving at a constant speed in a straight line. Now, if all moving clocks run slower by the same amount, then we should just have to say, in a certain sense, that time itself appears to be slower in the moving train. All of the phenomena in the moving train, the person's pulse rate, their thought processes, how long it takes to grow up and get old, all of these things must be slowed down in the same proportion in order to preserve the principle of relativity. This difference in elapsed time between stationary and moving frames of reference is referred to as time dilation, and is one of the great predictions of Einstein's theory of special relativity. Now, you might have been wondering what happens to the tick-tock of the moving clock as v approaches the speed of light. Well, we see from the equation for gamma that as v approaches c, gamma approaches infinity, and therefore t tends to infinity. In other words, the tick-tock of the moving clock would get slower and slower and slower until it would eventually freeze, and time would literally stand still. But we will come back to very fast-moving objects later. For now, we want to answer a simpler question. If all of this is true, then why don't we notice the slowing of time on a day-to-day basis? To answer this question, let's consider an example. Imagine that Usain Bolt is running the 100 meters and is travelling at an average speed of 10 meters per second. If I am stood at the side of the track and I observe Usain Bolt run past, by what factor do I observe time slow down? Well, we can calculate the answer. We know that t equals t0 divided by the square root of 1 minus v squared over c squared. And in this example, v over c equals 10 over 300 million. But we need v squared over c squared, which is 1 over 900 trillion, which is an incredibly small number. And therefore, 1 minus this incredibly small number gives a number which is very, very close to being 1. And so we see that t is essentially the same as t0. And this is true for the vast majority of moving objects that we encounter in our lives. They are simply not moving fast enough for us to notice the time dilation effect. So how do we know whether time dilation is real? Well, it turns out that a very interesting example of the slowing of time with motion is furnished by a certain class of fundamental particles known as muons. Muons are created when cosmic radiation bombards the Earth's upper atmosphere, and the muons created in the upper atmosphere spontaneously decay after an incredibly short average lifetime of 2.2 microseconds. Now, it should be clear that in such a short lifetime, the muons should not be able to travel much further than roughly 600 meters, even if travelling close to the speed of light. And yet, although the muons are created in the upper atmosphere some 10 kilometers above the surface of the Earth, they are actually detected in laboratories here on the ground. So how can that be? Well, the answer is time dilation. If, for example, a muon is travelling at 99.8% the speed of light, then we can substitute v equals 0.998c into the time dilation equation, and we see that the muon lifetime is increased to roughly 35 microseconds, during which time it is able to travel over 10,000 meters and reach a laboratory on the surface of the Earth. Okay, so let's assume that we are willing to accept the validity of the time dilation equation and the notion that time runs slow for moving clocks. Our next task is to understand how this links to Einstein's most famous equation, E equals mc squared. To this we now turn. Our strategy for determining the relativistic energy of an object is to first think about how we define energy in classical physics. We know from classical mechanics that if a force acts on an object causing it to accelerate from one location x1 to another location x2, then we can determine the gain in kinetic energy by calculating the work done, which is equal to the integral of f dx, where dx represents a small displacement along the path connecting x1 and x2. Next, we can make use of Newton's second law and rewrite the force as the rate of change of momentum, dp by dt. We also know that momentum is defined as the mass of an object multiplied by its velocity, and therefore, if we consider being in the rest frame of the moving object, then we can write p equals m dx by dt naught, where m is referred to as the rest mass of the object. Next, we can use the chain rule to rewrite dx by dt naught as dx by dt multiplied by dt naught. And if we then differentiate t with respect to t naught, then we simply get an overall factor of gamma, and therefore our expression for momentum becomes gamma times mv. Or if we write the full expression, we get mv divided by the square root of 1 minus v squared over c squared. Now that we have an expression for the relativistic momentum, we can differentiate this with respect to t to find the relativistic force acting on our object. To do this, we will make use of the product rule, which simply states that if we have two functions a of t and b of t being multiplied together, then the derivative of the product ab is simply a times db by dt plus dA by dt times b. Applying this to our example, we see that v is playing the role of a, and 1 minus v squared over c squared raised to the power of minus 1/2 is playing the role of b. Applying the product rule, we find the following ghastly green expression. Next, we want to calculate the highlighted derivative of 1 minus v squared over c squared raised to the power of minus 1/2. If we do this, then we find the following blue expression, which simplifies to v over c squared dv by dt multiplied by 1 minus v squared over c squared raised to the power of minus 3/2. So if we put this all together, then we find the following yellow expression for the derivative of the momentum. Note that both terms in this expression contain m times dv by dt, and so we can factor this out to arrive at the following green expression. The next trick is to write this as a single fraction, with denominator 1 minus v squared over c squared raised to the power 3/2, as can be seen in the blue expression. And we notice that the v squared over c squared terms in the numerator cancel. And so when the dust settles, we finally find this simplified pink expression, which is simply equal to gamma cubed m dv by dt. Now that we have a concise expression for the derivative of the momentum, we can substitute this back into our integral and finally determine an equation for the kinetic energy of our moving object. So if we combine everything that we've calculated so far, we find the following expression for the kinetic energy. The trick to solving this integral is to change variables so that we are integrating with respect to v rather than x. If we do this, then we can rewrite dv by dt times dx as dx by dt times dv. This change of variables will also change the limits of the integral, and if we imagine that our object begins at rest, then we can write v equals 0 at x1. Furthermore, we will assume that the velocity at x2 is v. If we sub this back into our integral, then we find the following relatively simple green expression. If we then integrate with respect to v and sub in the limits, we finally arrive at this pink expression. So let's now take a closer look at what this means. After a slightly lengthy calculation, we have arrived at the following equation, which tells us the kinetic energy of an object with rest mass m moving at a velocity of v meters per second. What we now want to do is understand each of the terms in this equation. The first thing to note about this equation is that we can, if we want, write this equation in a slightly more compact form as mc squared gamma minus 1. Next, let's see what happens when we set v equals to 0, in other words, when the object is stationary. In that case, we see that gamma equals 1, and therefore we see that the kinetic energy is equal to 0, as expected. Our equation gives the correct answer for a stationary object. But what else is this equation telling us? To reveal the true depth and power of this equation, we can rewrite it as mc squared over the square root of 1 minus v squared over c squared is equal to the kinetic energy plus mc squared. And this expression is simply equal to E, where E is the total energy of the object. So we see that the total energy of an object of rest mass m moving at velocity v is equal to gamma times mc squared. Now we wish to understand what this equation means. Well, in order to get a better idea, let's first write the total energy as mc squared times 1 minus v squared over c squared to the power of minus 1/2. If we assume that the velocity v is much lower than the speed of light, then we can expand this bracket by making use of the binomial theorem and arrive at the following blue expression. Because v is much lower than c, we can ignore all terms higher order than v squared over c squared in the expansion, as these will be negligible. If we then simplify this expression, we find in the low velocity limit that the total energy is equal to mc squared plus half mv squared. We immediately recognize the second term in this expression as the classical equation for the kinetic energy of an object of mass m moving at velocity v. So what about the first term? What does mc squared represent? Well, firstly, notice that this term appears whether the object is moving or not. If we set v equal to 0, then we see that the total energy of the object is equal to mc squared. Since this energy exists even when an object is at rest, this energy is referred to as the rest mass energy. how should we interpret this new rest mass energy? Well, even before the advent of relativity, it was understood that the energy of an object is more than just the kinetic energy of the object. Kinetic energy is the energy due to motion of an object, but even when the object is at rest, it may still contain energy. That energy was thought of as the energy needed to assemble the system. Now, what is particularly interesting about this assembly or creation energy is that it does not depend on the velocity. It is an entirely different form of energy. You can think of the rest energy of an object as the energy required to create the mass of the object. The more massive an object, the more energy is required to create that mass. Once this mass is created, you can think of the rest energy as a form of stored energy. Energy is being stored in the form of mass. Now, it is possible to release this mass energy in certain circumstances. This is, for example, how stars produce their energy, through the conversion of mass into energy during the process of nuclear fusion. We also know that if a matter particle encounters its antimatter partner, for example, an electron encounters a positron, then the mass of both particles will be converted into energy in a process known as annihilation, and the amount of energy released can be calculated using E=mc². We see that in the case of an electron and positron annihilating each other at rest, the energy released is 1.6 times 10 to the minus 13 joules, which may seem like a small amount of energy, but it is roughly 75,000 times the ionization energy of a hydrogen atom. If that doesn't mean anything to you, don't worry, let's think about it in a different way. If we were to annihilate 1.2 kilograms of matter with 1.2 kilograms of antimatter, then that would release 2.2 times 10 to the 17 joules of energy, which is roughly the annual energy consumption of New York. And all we would require is 1.2 kilograms of antimatter. Unfortunately, antimatter is not so easy to produce in large quantities as it quickly annihilates with matter. So this is not currently a feasible option for mass-scale energy production on Earth. So let's just pause a moment and take stock of what we've seen so far. We have seen that for a freely moving object of mass m with velocity v, the total energy of the object is given by E=gamma times mc². And by looking at the low velocity limit, we see that this total energy is comprised of essentially two parts: the kinetic energy of the object, which depends on the velocity, and the rest energy of the object, which is the energy required to create the mass of the object. It is this rest energy equation that is perhaps the most famous equation in all of physics, and we now see where it comes from and what it means. For any object, whether it be an elementary particle, a star, or a black hole, if we are in a frame of reference in which the object is at rest, then the energy of that object is its mass times the speed of light squared. This is perhaps one of the most profound realizations in the history of physics. Okay, but let's now focus on the situation where the object is moving. Well, in that case, we have seen that the appropriate equation to use for the energy of the object is E=gamma mc². So if you think about it, this should really be the famous equation that everybody knows about, as it is the most general expression we can write down to express the energy of an object moving with any velocity below the speed of light. Why do we say below the speed of light? What happens if we try to increase the speed of a massive object all the way up to the speed of light? Well, we see from our definition of gamma that if v tends to c, then gamma tends to infinity, and therefore the energy tends to infinity. In other words, it would require an infinite amount of energy to accelerate a massive object to the speed of light, and this is simply not possible. And therefore we see that the speed of light represents an upper limit to the velocity an object can possess in our universe. We can visualize this universal speed limit by plotting the kinetic energy function for a relativistic object and comparing this with the classical kinetic energy. According to classical physics, an infinite kinetic energy would require the velocity of an object to tend to infinity, whereas we see that according to Einstein's theory of relativity, the kinetic energy tends to infinity when the velocity tends to a finite number, namely the speed of light. And therefore we see once again that the speed of light represents a fundamental limit to the velocity of any object. So far, we've only looked at the properties of massive objects. These are objects that when brought to rest have a non-zero rest energy. But not all objects have mass. For example, we know that the fundamental particles of light, known as photons, are massless particles which travel at the speed of light. So what do we get for the energy of a photon if we substitute in m equals 0 and v equals c into the equation E equals gamma mc squared? Well, we see that in this case, both the numerator and denominator are equal to 0, which isn't particularly illuminating. Or maybe it is. Perhaps this is telling us that we shouldn't think of the energy of a massless particle in terms of velocity, because in that case, we would expect all massless particles to have the same energy since they all travel at the same velocity. So this leads to a natural question. Can massless particles have different energies if they all travel at the same velocity? Well, it turns out that the answer is yes. But in order to see this, we will need to look at the energy of a particle in a slightly different way. Instead of expressing the total energy of an object in terms of its velocity, we can rewrite the energy in terms of the momentum of the particle. This is something that is already familiar from classical physics, where we can take the expression for kinetic energy, half mv squared, and then using the definition of momentum, P equals mv, write this as ke equals p squared over 2m. So let's try doing something similar for the relativistic energy. If we take the equation E equals gamma mc squared and square both sides, we see that E squared equals m squared c to the 4 divided by 1 minus v squared over c squared. If we are a bit clever and add the following green expression, which is simply equivalent to adding 0, then we see that we can combine the first and third term circled in blue and write these two terms as m squared c to the 4 minus m squared c squared v squared all over 1 minus v squared over c squared. In other words, we can write E squared in the following form, and we notice that the term inside the bracket is none other than the relativistic momentum which we derived earlier. Furthermore, we can take out a factor of m squared c squared in the numerator in the yellow expression, which allows us to then simplify our equation, as can be seen from the green expression. When the dust finally settles, we see that the total energy can be represented by the famous energy-momentum relationship E squared equals p squared c squared plus m squared c to the 4, which should be familiar to anyone who has ever studied particle physics. We see that this expression gives the energy in terms of the momentum and the mass. The advantage of this is that it describes all particles whether their masses are 0 or non-zero. And the added bonus with this expression is that we can immediately see what happens if we set the mass equal to 0. In that case, we see that the second term in the energy-momentum relation becomes 0, and therefore the energy of a massless particle can be written as E equals pc, where p is the magnitude of the particle's momentum. Now you might be worried that according to the classical definition of momentum, in which p equals mv, that if a particle is massless, then its momentum must be 0. But this is no longer true according to relativity. A massless particle does carry momentum, and the magnitude of the momentum is simply equal to the energy of the particle divided by the speed of light. As an interesting side note, we see that if we combine the relativistic expression for the energy of a massless particle with the famous equation for the energy of a photon as proposed by Einstein to explain the photoelectric effect, then we see that the momentum of a massless photon can be expressed as Planck's constant divided by the wavelength lambda. And it's fascinating to note that in 1923 it was this equation that Louis de Broglie suggested applied to all matter particles, which then inspired Schrödinger to develop his famous quantum mechanical wave equation. To end, I would like to make one final observation regarding the energy-momentum relation. This equation lies at the heart of modern particle physics, and it's interesting to understand why. As I'm sure you've heard before, both the energy and momentum of an isolated physical system are conserved, which is simply another way of saying that the total energy and the total momentum of an isolated system do not change with time. And this is true from every observer's point of view. However, according to Einstein's theory of special relativity, different observers moving relative to one another will assign a different amount of energy and momentum to the system. The remarkable thing is that if those different observers then substitute their own particular values for the energy and momentum of a moving object into the energy-momentum relation, and then calculate the mass, they will all measure the same value, irrespective of their frame of reference. And so we see that the mass of an object is a fundamental invariant of the theory of relativity, something that all observers can agree on. And it is this fact that helps particle physicists to determine the masses of fundamental particles, because by experimentally measuring the energy and momentum, they are then able to use the energy-momentum relation to determine the mass invariant. It was by using such a method that the Higgs boson was experimentally discovered and the mass determined in 2012, a topic I will be returning to in a future video. For now, I think it only appropriate to leave you with the wise words of Albert Einstein. The important thing is to not stop questioning. Curiosity has its own reason for existence. One cannot help but be in awe when they contemplate the mysteries of eternity, of life, of the marvellous structure of reality. It is enough if one tries merely to comprehend a little of this mystery each day. I hope this video has helped you to comprehend a little of the mystery of relativity. Thank you for watching.